Hello, welcome to the third part of week 8 of the ECE 9013 course. In this part, we will be discussing constant complexity class, linear complexity class, and quadratic complexity class. So starting off with the constant complexity class, as the name suggests, this class has a complexity that is constant, that is, complexity is independent of the input size. There are very few interesting algorithms in this class, but can often have cases that fit this class. Some of these algorithms have loops or recursive calls, but only if the number of iterations or calls is independent of the size of the input. Often, we refer to the main operations to have a constant complexity. The second class is the linear complexity, which we often refer to as O of n. An example of this kind of algorithms is a simple iterative loop algorithms that are typically linear in complexity because the number of iterations is dependent on the exact number or size of the input. As an example, let's try to search in an unsorted list. So assuming we define the function to take an input list and an element, and we start with whether found is false, then we say that for every element or index I in the range length of L, if E is equivalent to L at I, we change this to true. If not, we return back to the for loop. So if we look through all of the elements, or we must look through all the elements to decide if it is there or not. So the order is of the length of L for the loop, multiplied by order of 1 to test if E is equal to the element at index I. So adding them, we would get 1 plus 4n plus 1, which is 4n plus 2, which is order of n. So the overall complexity is O of n, where n is the length of L, or the length of the list. Similarly, assume that the list is sorted. So again, we would need to look until we reach a number that's greater than E. We would still have the order of length L for the loop part multiplied by O of 1 for the checks. Note that here the order of growth is the same, though the runtime may differ between the two search methods, because in this case we can actually stop at the prior stage. So searching a list in sequence to see if an element is present has a linear complexity. We can actually add characters of a string assumed to be composed of decimal digits, and it would also have a linear complexity. So this is another example of a linear complexity algorithm. It's often the case that algorithms with linear complexity have one type of loop which depends on the number of iterations. So for example, in this case, the number of times around the loop is n. The number of operations inside the loop is constant. For example, in this case, it's 3. So again, the overall order of complexity is O of n. So if we mention or if we assume that simple loops typically have a linear complexity, what happens if we have nested loops or loops within loops? For example, if we have one nested loop, this can result in a quadratic complexity because, for example, in this case, what we're trying to look at or trying to find is if one list is a subset of the other. So if we're trying to determine if list 2 is a subset of the first. That is, every element of the first appears in the second with no duplicates. So here we can see that there are 2 for loops, and within the second loop, or for every iteration of the outer loop, we have n iterations for the inner loop. So the outer loop, for example, in this case, would execute length of L1 times. Each iteration will execute the inner loop the number of times length of L2. Therefore, the overall complexity is length of L1 multiplied by length of L2. The worst case would be when the lengths are the same, which would result in a quadratic order of complexity, length of L1 squared, or O of n squared. To find the intersection of 2 lists, we would also have to have 2 for loops, nested loops. So again, in this case, we would have the order of complexity to be length of L1 squared. Although here we have another for loop, this will be linear and this is quadratic, so the dominant term is the quadratic part. Here is another example. So here, to compute n squared, we are doing it in a very inefficient manner. However, typically when we deal with nested loops, we look at the ranges. With nested loops, each iterating, for example, n times, we would have n squared, and this can be extended based on the number of nested loops existent. Thank you.